Recording. Okay, so hi everyone. Today we're going to cover oracles. Oracles are a key part of the blockchain, especially because we need some way to get information from outside the blockchain. So currently, we have the way that we do this is through oracles. The way that we implement these oracles depends on, like, there are many ways of implementing, both centralized, decentralized, etc. Today we're going to do the simplest one, which is like a centralized oracle. There's someone, let's see, I'm going to share my screen. There's someone in charge of the oracle.
Is it only me or? Ah, there you are. I can't hear you. Hi, Albertina.
Sorry, for some reason I tried to share my screen and the Chrome just collapsed. Sorry. You were saying something, Lars?
No, I was just wondering whether it's just me that doesn't hear you anymore.
Okay, let's try once again. Let's share my entire screen. Okay, good. It worked. So, as I was saying, so oracles are the way that we input information from outside, from the real world, into the blockchain. By themselves, they are not really useful, but the usefulness comes from providing data to other smart contracts. So if you have, for example, a smart contract that to bet on, like, football matches, you could, for example, like, lock it and say, okay, it's going to win it's going to if the team A wins, I get twice as much, and else I lose the money. And then there's like a counter, like a person that bets the opposite, and that's where the money comes from. So, for example, and then that validator needs some way to check where if after the match, which team won, the team A or the team B. So that's what an oracle does. The oracle is going to provide the information. For example, the information that the team A won. And then based on that, the person 1 or person 2 is going to be able to take the money from the oracle. So the person that actually won the bet. This is not an ideal solution, because who is in charge of the oracle? For example, if someone, like, random person is in charge of the oracle, anyone could, like, that person could just say, okay, team, I'm going to bet on the validator, and I'm going to provide a response that I wanted, that I needed to win, so I'm going to win. So it's like you can game that. So there are solutions for that. I mean, one example is still a centralized oracle, but a better option will be, for example, if it's a World Cup match, to be able, like, the only way to update the state of the oracle, it will be, for example, to if both the World Cup president and both teams sign the transaction of team A1, for example. And with that solution, you get at least some sort of agreements between between everyone involved in that football match about who won. And that will be, for example, one of the solutions, still centralized, because still depends on like the entities, but I think in that case will be fine. But then a more interesting case will be the value of, for example, how much dollars is one ADA, or how much ADA is $1. The rate of a coin. And that's much more important for us, like financially, and that's what we're going to do right now. So we're going to create an oracle that gives you the rate of US dollars for ADA, something like that. Then this is a standalone lesson, but next lesson is we are going to implement a stable coin. And in that lesson, we're going to use an oracle. So you should understand this lesson for then to be able to understand, at least conceptually, so you can then understand the stablecoin lesson. So how do we actually implement an oracle? So we need, as everybody knows by now, a UTXO is unique. So we need a way, for example, let's say that I create this UTXO in a validator, and this UTXO says that the rate is like 10 USD ADA. We're all rich. So everyone can see well. Oh, should I zoom? Just a bit. Okay, so I create this UTXO. This is now, this information is inside the datum of this UTXO and is inline. So datum, and everyone can read this information. But the thing is that I have to give them like the address of this information. Where is this information living in, right? And if I tell you, okay, this is the datum, this is the reference of the UTXO where the datum contained information is, you could find that information, that we find, but I cannot update that information never ever again. Because as soon as I create a transaction, that consumes this datum and then create a new one with like 12 USD ADA. Now, all of a sudden, wait, there you go. Now, all of a sudden, you don't have the address of this new datum. So how can we solve this? We talked a little bit about this in the previous lesson. So many of you already know the answer. What do we do so to make sure that no matter how many times the datum is updated, I still can find it? Anyone? How can I do that? We already spoke about this in the last lecture briefly. Now we're going to actually do it. But anyone remembers? We need a way to find this information that is unique.
I remember.
I know you do. I know you do. Oh, sorry. I have to pause. Okay. So someone that is not already an expert.
I don't know if this is the same solution as the solution that we have in the last lesson, that we had to attach this information on the datum of the UTXO, or the other one to create an NFT or something like that.
Yes, very well. So these two, what about the first one? For example, if I attach any sort of information, extra info to the datum, you still won't be able to find that datum because you need to know where the datum is to get that information. But I can, as you said, I can add inside, like in the UTXO, I can add as a value, let's see. An NFT. So now, if I consume this UTXO and I create a new UTXO with the new information, I can make sure, if I make sure that this NFT is, when I create this transaction, I make sure that this NFT is consumed with the UTXO and is now put into the new UTXO, new output. So this is the same NFT that is being consumed in the transaction, and like it's been moved from the previous output to the new output. If I can do that, I have something that is unique because the NFTs are unique by definition, and that is moving around with the last updated value. So this is the current solution, exactly as you said. So we want to have something unique, and we chose to use this NFT. So we're going to create an NFT. We're going to put it in the Oracle. This is the UTXO Oracle, the Oracle's UTXO. And we're going to move it around with every time we update the Oracle. So now, anyone that wants to know what is the current state of the datum, what is the last value of USD ADA, the only thing they need to do is to find the NFT in the blockchain. If you find the NFT, wherever that NFT is sitting, the datum of that UTXO is going to tell you the current value. Make sense? We have a question?
No, it's a question.
Okay, thank you. So now our job is to create the Oracle in a way that we have to make sure that these NFTs passed around when updating the datum. And also we have to make sure that the datum has the correct shape, because if we were able to create, instead of, for example, the actual value is going to be 12, for example, 12. But then if we change this to nothing, for example, or if we change this to a string or a scream, now the datum is like worthless. So we want to check that at least that that is a number. We want to check that at least like both in all the time. These are numbers. So The first thing that we're going to do then to get started is the Oracle's owner there's an owner, and let's see if I can zoom. Yes. So the Oracle in this case has an owner because as we said before, this is like the simplest implementation, the centralized one. There's someone in charge. And to use like for people to use that Oracle, they have to trust that person. So we have the Oracle's owner wallet, and this UTXO is like in the Oracle's owner's wallet. And the first thing we're going to do is to we're going to create a transaction. Let's see how this is called. We're going to create a transaction that is going to create, it's going to mint is going to mint an NFT. So now the Oracle's owner's wallet is going to have an NFT. And then with that NFT, we're going to create an Oracle. We're going to create an Oracle. The first thing we want to do is to, let's see, create a new, the Oracle owners having already minted the NFT is going to create an output in the Oracle's address containing datum, a number, and as a value, the NFT. And for reasons that we didn't discuss, on top of the NFT, there has to be a minimum amount of ADA locked to prevent exploiting the blockchain. So, sorry, we have to do the transaction. Or I can just copy this one. So this is going to be a minting transaction to get the NFT. Then we're going to send the NFT in a new transaction to the Oracle address. And then we'll see. We have two options here. What could we do with this Oracle? I mean, we know that we want, like, the price is always changing. So we know that we cannot just maintain that Oracle with the same number in the datum forever. So we have to have a way to update it. So there has to be a mechanism to update Oracle. And on top of that, we also want a way to destroy the Oracle. We want to be able to delete the Oracle in case it's not needed anymore. I mean, we could just leave it there and no one's going to use it. But we're going to implement also a way to delete the Oracle. So that's one, and that's the other. We also want to next, delete Oracle. So there's these two options. We already have the oracle. In this case, we like this transaction create oracle. And this transaction was mint NFT. So we have the oracle, and for example, to delete the oracle, I mean, we just delete it, right? So we want to like consume this UTXO that is sitting in the oracle's validator address, but we don't want to generate a new one. But the thing is, like, we want to make sure that no one can just delete the oracle. Just like specific person can delete the oracle, not everyone. So in our case, now the oracle's owner's wallet that doesn't have the NFT anymore because the NFT is sitting in the oracle. So now we need a transaction when the oracle's owner signs the transaction and text transaction delete oracle. And after this transaction, the oracle's owner wallet is going to contain the NFT again. And then like the oracle's owner can just do whatever he or she wants to do with the NFT. And the NFT is not longer sitting at the oracle's address, so it doesn't have the number. It doesn't like it's not being used anymore. So the oracle's owner actually should use the same minting policy that he or she used to create it. Should use it to like to burn it, to the same minting policy, mint, burn, so the NFT doesn't exist anymore, and that's it. So that's one possible path for the oracle. The other path is to update it, which is like the useful thing. We want to keep the value updated. So to be able to update the oracle, again, the owner needs to sign the transaction, of course, because not everyone can modify the oracle. And let's see, let's copy this. So let's create transaction of update oracle. In this case, we need to create another oracle output in the same oracle's address, but having an, let's zoom in, updated number. And then, like from, of course, the NFT, now it was previously in this UTXO that got consumed, and now it's here. Now it's here. The NFT is still sitting at the oracle's address, but now the datum has been, like the number in the datum has been updated. So we need to do all this. Luckily, we already covered NFTs. So this part, you already know about this part. We won't cover this part because like we're going to reuse the same validator that we used for this lesson. So we need only one more validator. We need only the Oracle validator. and we need to be able to create an initial output from the Oracle's owner in the Oracle's address. We don't need to like convey this in the actual like logic of the validator, because as we said many times before, the validator only cares when you are consuming a UTXO in its address, not when you are creating a UTXO. So in this transaction, you can see that we are not consuming an Oracle's UTXO. We are consuming only the owner's wallet, like an UTXO that contains the NFT in the owner's wallet. So we don't need to specify any logic in the actual Oracle smart contract, because this creating transaction doesn't consume a UTXO in the Oracle address. Once we have it, though, in both cases, both updating the Oracle and deleting the Oracle, we consume an Oracle, a UTXO in the Oracle's address. So both cases needs to be accounted in the validator logic. So those are the two cases we want to coding. One to update and one to delete the Oracle. I think that's it for the overview. So from now on, like all we're going to do is to like actually build the code of the Oracle, and then we're going to actually run it. Any questions about the like really high level overview? Okay. So let's start coding. Let's zoom in a bit. So I have some notes about what I just said. So this is what we want. We're going to write a script that is a simple Oracle that can be updated or deleted by only the operator. To delete the Oracle, we only need to check that the operator must sign the transaction. We don't care about anything else. And to update the Oracle, we need to check many things. We need to check that we consume like exactly one Oracle input, and that Oracle input has to contain the NFT. I mean, by definition, if we consume an input that contains the NFT, is the only one that contains an NFT. But by doing this check, we can fail early if we don't find the Oracle's input as any Oracle input. We have to also, we have to produce in the transaction an Oracle output, and this Oracle exactly one, because this Oracle output has to contain the NFT. And the Oracle datum, the datum, we chose it to be like an integer. We could create like a more complex structure containing more like structured and varied data. We chose it just to be an integer. And then the transaction to update the Oracle must be signed by the validator. Okay? So first thing we need to do, as always, we need to write a validator. We're going to start like this. We need to write a function. This function is going to be called Oracle. And because this function, we want this function to be an Oracle, to be a validator, we promote it by putting it inside the validator block. This validator block is telling, hey, this function is now promoted to be a validator, not just a regular function. And because it is a validator, it needs a datum, because this is a consuming validator. We are writing the logic to consume, to spend a UTXO. So we need a datum, we need a redeemer, and we need a context. Of course, like all validators, it returns Boolean. True if we are able to consume it, false if we don't. We don't have script context, so let's add it. Okay, so first check. As always, the first check is really simple. We need to check if we are actually expanding something. So when we need the context now, so let's uncomment the context. When context, oh, I have Copilot. Let's see. Good. So when context, and now we did it a bunch of times. What comes next? Someone? Let's see. Yes.
We
No,
have
not-
to. Okay. We have to check the purpose of the context, the
Perfect.
transaction.
Perfect. Exactly. Transaction purpose. And that purpose can be many things. We only care about spending purpose. When for now, we're going to ignore the UTXO. And the spending purpose to do. And for anything else, we can just say fail. We can return false. And that's fine because like the whole function is going to return false. And the validator return false, and that's it. We can also return like fail. This fail function is one of few that has the real side effect of like failing the computation right on the spot. So we can just say fail and here add like a text, like an explanation. Like this can only, this validator only cares about spend. Only allows. For example, and now we have to import.
You probably explained that before, but what does the add symbol do?
Yes, see, I actually don't recall if I actually explained it. So thank you, Lars. So we have many ways, many different types that could be represented as something that we read as strings, as a bunch of text. So this symbol on front tells us the actual type of the text that we are reading. If we have the @ sign, this is a UTF-8 encoded string. If we have the, there you go. This numerator, it means that it's a byte string. And if we have nothing, I believe there is still a byte string, but it's not hex encoded. It's just string. So something is, let's see, actually, if we can check that, I believe, in the documentation. But yeah, that just indicates the type of string. In this case, this is a rare case where we actually want a UTF-8 encoded string because we want to be able to read this in case of failure. So if we do this, if we use this hash and we get like the byte string, if this validator fails while using it, we won't get this nice string. We will get the encoded string, so we will get gibberish for us. We won't understand what's that. So if we actually like put the @ sign, this is going to be encoded as a UTF-8 string. So when the validator fails, we will have this nice explanation about why it failed. And
Nice, thank you.
welcome. Docs. Let's build Aiken docs. And Yes, that's just a warning. Serve box 8,000. And oh, I lost my. Well, let's see. Where is it? Okay. So let's move this to where I want it. No. So now I just, there you go. This string. No, we have to standard. Let's see if we can find it. Yeah, so here, as you can see, we have something like looks like a string, redeemer.message. But as you can see here, we don't have the @ sign. So this is actually a byte. Whoa. So this is actually a byte array. And if we actually go to the type, we see that it's a byte array. So that's how we can, it's really friendly actually. There you go. So from byte array. So as you can see here, there are ways to convert, but it's not like, because it's not a total function, it could fail. It's lagging. For some reason, my screen is lagging. So let me know if it freezes. So yeah, that's the difference. That somewhere in the documentation explains like the 3 differences, but these, like without and with the hash, they are byte arrays, and with the @ signs, they are actually UTF-8 encoded strings. So let's keep moving. So we can do this, and this is also really useful. For example, if the strings are really useful, we can say trace, and we can add, we are spending, and now we have a trace, like whenever this part of the contract is evaluated, it's going to generate a trace. And we will know that we are actually, like, we reached that point. This is like a more verbose way of writing the contracts. It's really useful at the very beginning, and when you actually compile the contract, if you just do Aiken build, this trace is going to be erased, and this string is going to be erased as well. It's just going to, it's like fail, and that's it. So because we are building for production, and this is expensive to have these messages that they don't add anything to the actual logic of the smart contract. So those are erased by default. There's a flag that you can activate that I actually did when developing the I did when developing the stablecoin that we're going to see next lesson, that allows you to leave those traces on. So when you actually use the contract, you can see the traces if it fails, or if it not, like it doesn't as well. So let's go back to the Oracle. In the case that we're spending, we also have like 2 possible ways. So we could be either updating the Oracle or deleting the Oracle. And actually on that, for that reason, we need to provide a type, and we need to we need to provide some way to know the Oracle, hey, our intention is to update, or our intention is to delete the Oracle, the information, and based on that information, the Oracle is going to do one check or other. So the way that we provide the action that we want to do is we're going to create a type. And this type we're going to provide as a redeemer. So we're going to say Oracle redeemer. And remember that if we want to have just one constructor, we can just avoid writing the whole constructor. So here we can have two different types, so update and delete. So those are the two things that I want to do. And it's complaining that I'm not using it, so let's use it. Let's say the redeemer is Oracle redeemer. So now I'm actually using the Oracle redeemer, but I'm not using the constructors, not using anything yet, actually. Also, we said that in the datum, we want to save an integer that it represents the rate. So here in the datum, we could say int to say, okay, I'm going to save an integer there. That's the information that we want to convey to the blockchain. But we could also, like, just to generalize it a bit and to have more, to be more clear about our intentions, we can create a synonym type called rate, for example, that is the same as int. So the representation is actually the same, but the name is different. So we know that we're not talking about any integers. We, the developer, we are just talking about specifically about the rate. So we have our datum, we have our redeemer, our context. Let's start. So if we are spending, we want to check what we are doing while spending, like what's the option. So when the redeemer, maybe I should call this redeemer to be clear, and datum, and when the redeemer is, and now we have two options. The redeemer can be either update or delete. So also, like, small comment, you can also add you can also add strings to your to-dos, just if you need it for some reason. The to-dos are actually semantically the same as fail. The difference is that the compiler is going to allow you to compile because it's assuming that you are not going to use that part. If you happen to use that part, it's because you forgot to implement it. It's going to fail anyways, but it will let you, like, actually compile and test the validators. That's the difference between. So it's a use case thing, but both the to-do, if you forget to actually implement something, or if you fail, both in the blockchain will fail. So we have the redeemer. We can both update or delete. So I think actually let's do delete first, because delete is easier. So what did we say about deleting? Let's go to the top. We said that to delete the oracle, we only check that the operator must sign the transaction. That's the only thing we care about. So we already did this like 157 times already. Do you remember, anyone remembers where are the list of signatories that signed the transaction? Anyone remembers?
I think it is in the transaction extra signatories.
Yes. Perfect. Thank you so much. Let's do it. Transaction. So if we go to transaction, and transaction is inside the script context. So we have the script context, we have transaction, and inside transaction, we have a bunch of things, extra signatories. So exactly, that's where they are. So we can say context transact. These are the extra signatories, and now we have to compare these extra signatories with the owner of the oracle. But we don't have the owner of the oracle. Like the validator doesn't have access to who's the actual owner, has access only to who signed the transaction. So we have to provide the oracle owner in some way. For now, we're going to create a new type called oracle parameters, params. And inside these oracle params, we're going to say operator. And this operator has the type list of hash on Blake, blah, blah, blah. And actually, that's too long. It's not a list. So the operator is of type hash. Oh yeah, no, I thought it was in Neowim. So no, I'm this code and I have to import with this weird thingy. Okay, so the operator is a hash Blake verification key, which is a bit verbose. So we're going to do a type alias again. Type, we're going to call it Pookie hash, which is the same. Pookie hash. All right, so that's more readable. And these are, the oracle is going to be parameterized by the operator. That means that doesn't matter how many times or in which ways I'm going to update the datum, consume it, and whatever. If I parameterize the validator in a way that the operator is in the parameters, no matter what I do after this, once it's deployed, only this person is going to be able to update this oracle. This could be good or bad, depending on your opinion, but for now, it's our choice. There's a single owner that's going to be always the owner, and it's going to be always the same Pookie hash. So we're going to parameterize the validator. And now delete here. So now we want to, this should be erroring. What is not erroring? It is
In the line 20, I think you have a comma in the last.
in the line 20.
Yeah.
Oh, thank you so much. There you go. Now it's erroring. Thank you, Karina. Thank you so much. Now we have an error because this is not a Boolean. We're not returning a Boolean, so we need to figure this out. So we have now the operator, and we have a list. We have the Pookie hash and a list of Pookie hashes. We already saw this, but we're going to search it anyway. So inside, oh, there you go. We have here the list. We have all, any, blah, blah, blah. Has, I think was it. Has key. Again, it is has. So let me look for it. For the right, has. So figure us out whether a list contains the given element. Same as we did with all the last two validators. We're going to use this to check if the operators, the owners of the Oracle, is one of the persons that signed the transaction. So we can say list has, and it takes first the list and then the element. So first the list and then params dot operator. And now I have to import list. No, that wasn't it. And tx is context dot transaction. There you go. So now we have this has function that checks if the operator is inside the list of people that signed the transaction. And luckily, it returns a Boolean. So that's it. If it's true, if it's inside, it's going to return true, else false. So the delete part of our Oracle is done. Super easy. Now, let's go to the update part. There's a lot of things we need to do right now. So we said here on top that we want to consume exactly one Oracle input. So what's this Oracle input? How can we check that? So we are consuming at this point one Oracle output, and we have provided by the spend constructor the reference of the UTXO we're consuming. Spend. The reference here, the output reference of the UTXO we are validating right now. So we can use that reference to check if we have like the Oracle's input. So let's say, let's name this this script output reference. So this is the reference of the UTXO we are validating right now, like when running this script. So now, how can we find the input? So if we search just to find input, transaction, there you go. So in Aiken transaction, we have this function called find input. Find an input by its output reference. Perfect, exactly. This is typically used in combination with the spend script purpose to find a script's own input. Perfect, exactly what we need. Actually, we have the implementation right here. So we could just copy and paste it, but we're not going to do that. We are going to actually write it. So where was it? Find input. And so we have the find input function. that we want to import. And this find input function takes a list of inputs, which if we go to transaction, and inside transaction, we have inputs, and we have the list of inputs. Perfect. So we have a list of inputs. So we can say context.transaction.inputs. Transaction inputs. And then we have to provide the output reference, which we already have. So this script output ref, and let's use a let binding. So the formatter let Oracle input equals, there you go. And we're going to add a to do, so we don't have the compiler annoying at us that we're not returning a Boolean. So we found the Oracle input we're trying to spend, but we get an option back. And if we take a look at option, I think we already did, but just in case, if we take a look at option, there you go. No, where's that? Choice. Maybe it's in the prelude. Option. There you go. So in the prelude, there's this Aiken type called option that is for returning optional results. It can be some and contain the value or none. So this is one-to-one, the same type as maybe. So we can have just something or nothing. So it's the same. So from now on, if we will just use the function, if we just use the find input function, we get an option input back. So from now on, you will think that every time we want to use the input, we have to say, okay, if is some, do this. If it's none, do the other thing. Fail, basically. But we don't need to, because as we saw in the previous lesson, we have the expect function that allows you to partially pattern match instead of like doing a total pattern match for all constructors. We can just partially pattern match with the expect, and anything that is not the single constructor that we pattern matched means that the validator fails. So this is really convenient, because if we don't find the Oracle input, which should never fail, but if we don't find the Oracle input, we can just fail straight up. So instead of having this optional Oracle input, we can say sum, we pattern match for the sum constructor, and we will get an error saying that it's a bit weird error, but here, non-exhausting pattern match. Perfect. So because we're using the let keyword, so if we say expect, I expect that this has to be some. This has to be the same as just in Haskell. And if it's not, just fail. Like, I don't care, just fail the validator. The transaction won't pass. So that's what we can do with the partially pattern matching we expect. And the cool thing is that now, because we pattern matched explicitly for the sum case, we don't need to deal with the optional value of Oracle anymore. We are sure that if after this expression we keep going, we are sure that there was an Oracle input, because if there wasn't, the validator will just fail before reaching the expression that we are writing. So now we actually have the Oracle input. And now we need to check that this Oracle input has the NFT. The NFT that we said we're going to mint and send the first time. So every time we consume the Oracle, we have to check that it has the NFT to be sure that we actually consuming the right UTXO. We are removing the old Oracle. So now we need the NFT. We need to know which NFT is the one we are checking. So we need to provide the NFT again to the validator in some way. And we're going to provide it inside the parameters of the validator. So here we have to provide the NFT. And the NFT, like any token, is defined, it's the asset, it's an asset, and the assets are defined both by their policy ID, as we explained before, and the token name. Because one policy ID can mint different tokens with different names. But if you make sure that you have the specific policy ID for this specific name, you can be sure that that is a unique, that is a specific token. And if you know that that token could be minted just once and one token, you know that that token is an NFT. So we need two things. We need the policy ID and we need the name of the token. And we could say NFT policy ID, and then NFT name. We could do this and then like keep going, and we will have access to this. We have to, when we actually create the final validator, we have to provide the NFT. But we are going to join, like we're going to put this together in a single type. That is both because it makes sense, like we have a single type that logically encapsulates everything about an asset, but also because if you keep going with like Plutus and you keep writing and working as a developer, you will encounter this asset class thing. This asset class is the type that it traditionally, historically, in other languages like Plutus TX, was used to identify the NFT. And this is just what we just said. So the policy ID of the, which is type, of course, policy ID. And the name of the NFT, which it's a byte string, same as policy ID actually, because policy ID, it's just a hash of a Blake of a script credential, but as we have this thing called asset name, that is just a type alias for a byte array, but it gives us a clear definition of what we are using. So we are using an asset name. We have to import this and this. There you go. So this is how we're going to define our NFT. Everything, actually, not only NFT, but all tokens in Cardano, they are all native, and they are all defined by their policy ID and the name. So we can say NFT, and this NFT is going to be a type asset name. So now inside the parameters, there's not only the operator, but also the NFT. And why? Oh, because we're not using them. So now we have the NFT. We just have to take it from the parameters, and we can do it. So we have the asset class of the NFT. We have a way to identify an NFT, but we want to know if this specific transaction contains the NFT. So if we go to value, we have all the here we have, for example, the asset. There you go. The way that ADA is defined, I think Loveless is defined. We already explained this, but just a reminder, is defined both by the asset name and the policy ID. And in the case of Loveless, of ADA, is the empty byte array, which means that we don't, I mean, there's no policy, there's no logic able to mint or burn ADA. So there's a fixed amount on ADA and no one can do anything about it. So if we scroll, we have flatten from asset, from Loveless is 0, quantity of, extract the quantity of a given asset. So if we provide some value, the policy ID and the name of an asset, it will give us the amount of assets in that value. Okay, so we have the policy ID and we have the asset. So which value we want to take? Well, actually, is the value locked by the Oracle's input. If we go to outputs here, input actually, if we go to input, we'll see that input has the reference and an output. So now, oh, this right here. So we have this input. This input contains inside the output, and the output contains inside a value. And this is the correct type. So we can check if inside the value of the UTXO of the output we are consuming, we are validating right now, there's a specific asset. And that specific asset, in our case, is going to be an NFT. So now we're going to say, okay, quantity of, and this have to import it. So quantity of, and the quantity of took a value, a policy ID, and the name. So let's amount of NFTs, amount of NFTs, returns an integer. So this is of type int, and quantity of took first the value, then the policy, then the name. So the value, as we said, was inside Oracle input dot output dot value, and then we have the params dot params.nft. Yes, .nft, and inside NFT we have policy underscore ID and name. So params NFT, and first was policy ID, and then params.nft.name. And I think if I save policy ID, or params NFT policy ID, asset, let's say, first policy ID, params NFT policy underscore ID. Poly. What? I'm misspelling. It's the same, right?
Yes, it's the
What
same.
is it? Maybe I need to restart the server. Oh, Dino, no. Oh, I don't have one. Let's see. I have no idea why this fails. Params.nft. Oracle params. Policy.
You,
Okay, let's try.
I think you have to put the asset class instead of asset name in the Oracle params. In the
How-
Oracle,
Yes,
in the Oracle,
it must be
you have-
asset class, not asset name, the type of NFT.
Oh, got. Yes. Thank you guys so much. Thank you, Adrian. You're the second
You're
time
welcome.
I do these typos. Okay, so inside the asset class, we have the policy ID and the NFT name and the name. So this is the amount of NFTs that we have, and this should be exactly one. So we could like check this at the end. We could say like we've been doing up until now. We like build up a bunch of booleans, and then at the end we do the checks. But it's efficient and it's also easier to like fail in the spot instead of like keep going through the to the checks. It's better to just fail. I mean, if it's easier to read and to understand why we are failing, it's better to fail on the spot. So instead of like naming the amount of NFTs and blah blah blah, we can say we expect that this quantity of NFTs is equal to 1. So we can say 1 is equal to this quantity of NFTs. So here we're expecting 1 Oracle input. Here we expect there's exactly 1 NFT. Expect Oracle input has exactly 1 NFT. And then we keep going. So, okay, we have the Oracle inputs. we have like the input actually has the NFT. So now we need to move to the output side of things. So the input is fine. We need to move to the output part. Before that, do we want to make to do a small break? 10 minutes, or should we keep going?
Yeah, I think the break is good.
Wait, 10 minutes. It's okay.
Okay, we'll see you at 35 then. Okay. Anyone has questions, please write them in the chat and I will answer when I come back. Hi, everyone. Everyone is back?
I think.
Okay. Thank you, Karina. So we had a question during the break by Adrian. So could you please explain what is the purpose of this script out of ref variable and what information contains inside that variable? So this script output ref, it comes from like the spend constructor itself. And this is just the reference of the output we are validating right now. Every validator, the validator, like the logic we are writing right now, runs for every output we are trying to consume in the Oracle's address. So if for some reason we have 3 different Oracle UTXOs that we try to consume in the transaction, this whole logic, which is too big to fit in a single screen, but this whole logic and everything we're writing here is going to run 3 times. One for each UTXO we're trying to consume in this here. So in this transaction, we're going to validate the Oracle's owner's wallet by just this signature, so no validator is run there. But this transaction is also consuming this Oracle right here. So when we run this Oracle, when we run the validator for this specific Oracle, we have access to the reference of this specific Oracle. And if for some reason that in this case doesn't fit, but in others it could, like in other scenarios, you could consume multiple UTXOs from the same validator in a single transaction. So in this scenario, we have actually 2 different UTXOs from the same script. So this output reference that we have right here is going to tell us which of the 2 we are actually validating right now. So when we run it for this, we're going to have the reference of this UTXO, this output. And when we run it for this, we're going to have the reference of this UTXO. So we can have like different logic depending on like which output we are trying to consume. In this case, Oracle, as we said before, is unique. So this doesn't apply here, but in the testing lesson, we saw how we could consume multiple ones. So this output reference is just a pointer that tells you, hey, this is the output we are trying to consume, but has no other information. So if we actually go to here and we go to output reference, there you go. No, this is of type spend output reference. No, yes. Yeah, sorry. So it's okay. So this is of type output reference, and the output reference contains the transaction ID and the output index. So any transaction can create multiples, dozens, or even hundreds of UTXOs. But each UTXO, it has a specific index attached to it. So if you give me which transaction created the UTXO and the index of the UTXO, you can uniquely identify a specific UTXO in the blockchain. So this is the information that we have here in this script UTXO ref. By itself, in our specific scenario by itself, it's not really useful because I don't need the transaction ID for anything in particular or the output index for anything in particular. But because now we have a specific pointer, we have a specific pointer to a specific UTXO that is a unique UTXO, we can use the find input function and provide the reference. We can use the find input function and provide all the inputs that we have. We could have like dozens of inputs, but inside those dozens of inputs, I'm interested specifically on this one, like I'm going to give you the reference for a specific input. So thanks to having the pointer, the address of a specific UTXO, I can actually find the output itself. And once I find the output itself, now we're talking, because now once I have the output, now the output has inside this output that I found, I have more information, which is the address of the validator, of the address of where the output is sitting on, the value contained by that output, the datum of that output, and a reference script if it has any. So it's optional. So that's what's the point of using this reference, is to find the input we're validating right now. And once we have the input, that inside the input, there's an output, or this is on top of here. So inside once we find the input, we have the output reference, which is the one we already used. So like we already have this one, but it has the output with all the information we actually need. We need to check the value. We could check the address, and we will check the address in the next check. We could check the datum. We could do a bunch of different logic checks based on that information. So that's why we need. That's how we use this reference. Make sense?
Yes, it makes sense.
Awesome.
Thank you.
Yeah, you're welcome. So we got, now that we're here, let's do a recap. We took the reference of what we wanted to check. We chose to update the Oracle. And when we use this reference to find the input. Once we have the input, we are sure that we found the input. We check that the input contains the NFT. So the input is fine. Now let's move to the output, which is a bit more cumbersome because we don't have this find output function easily to use. So here, now I want to check same as we did for the input. I'm going to expect one Oracle output. So how can I find the Oracle outputs? I need to find not the inputs, but the outputs, the things that I'm going to create after the transaction. They are going to be there after the transaction. So this is a bit more cumbersome, but still not extremely complicated. So we have inside context, script context, we have transaction, and inside transaction, we have outputs with a list of outputs. So if we go to outputs, as we saw before, we have a list of all the outputs, and inside the outputs, we have an address, a value, a datum, and a reference script. So what we need here is there could be dozens, as I said before, there could be dozens of these outputs, but we want only the outputs that after the transaction are going to be sitting at the Oracle's address. So we want to check, we want to filter this list of outputs and maintain only the ones that only the ones that this address is the one of the Oracle address. Okay, good. So far so good. But we don't have the Oracle address right now. The cool thing is that we could get the Oracle address because we have the Oracle inputs. We got the Oracle input, and inside the Oracle input, there's an address there. And we can use that address to check that the outputs have the same address. So same address goes in, same address goes out, and because we know that that address is the Oracle, we go to the check. So it's Oracle input dot outputs dot address, and we are here, address, and we have something of type address. So let's address. So a Cardano address typically holding one of two credentials. So we have the payment credential and the stake credential. We haven't talked anything about staking, and we won't in this specific course because like 95% or more of validators are either spending or minting. So we won't like go in there. If you keep building on Cardano, you will eventually need to learn about like this difference. But Cardano has this duality, like parallel systems, that is like, and one ADA can be used both to spend, like to pay for stuff, and also to stake and like be part of the validation of the block validation process. And those are separate. So you have two different credentials to manage one or the other. So you can move your ADA around without like touching the staking part, and you can stake and unstake and change your staking status without moving your ADA around. So for our purposes, this validator has a unique payment credential, and that payment credential is the thing that we care about. So inside this validator, address.payment credential. So let's go now inside payment credential. My computer is going super slow for some reason. Payment credential is the same as credential, which is, it's an alias, which is not super helpful. So let's go to credential. Okay. So this payment credential is the same as credential, and credential can be either a verification key credential, which is like your regular old like wallet credential. So public key hashes, like people use wallets use this credential, and you can also have a script credential that contains the script hash, like the script credential hash. So we know that we are actually the address is from a script, and we are interested in this unique hash because this unique hash is the one that we want to compare to all the outputs. We want to get this hash because this is the one that we are sure that is the Oracle hash. So what we could do is that this is our payment credential. So we could expect that is a script credential to pattern match partially to script credential and give a proper name to this value. So then we can use it. So we have the payment credential, and we are going to expect that script credential that contains the Oracle hash, and that's it. So if we save and we import, and here we're going to tell like what we are doing here. We are getting the Oracle script hash. So now we have the Oracle script hash that we took from the one input that we are sure that is the Oracle's input. So now we have a unique way of filtering all the outputs. So we're going to say filter outputs to only keep oracles. Well, oracles once. So let's go. I think we need the filter function because we want to filter. Awesome. So I think we already used the filter function. But we provide a list, a predicate, and we are returned with a list. And if we see, when we filter, whatever the predicate returns true is the thing that we keep. So we want to check that we want to check that the oracles, like the nth output has the same oracle, the same hash as the Oracle hash. And if that's true, it's going to be kept in the final list. So we have the outputs. Let's say list filter. And we need to provide the list. So transaction dot context dot transaction dot outputs. So we have all the outputs now. We have all the outputs, and we want to filter them. We could create a separate function like outside, but because we're going to use it just once, it makes sense to just create an anonymous function. So we say function. This function is going to be applied to every output. So I'm going to call O for output. And this function is going to take this output. And what we want to do, we want to do again this part where it's here. we want to again this part that go and check in the script credential to get the outputs hash and compare it to this one. So we could do this in many ways, but because we are eventually we have to pattern match to extract the hash. We're going to pattern match from the get-go. So when the output, this is the same as what we did here. So output, address, payment credential. Actually, I'm going to copy and paste it. So if the output address dot payment credential, if this is, as we thought, a script credential, we're going to do something. And if it's not, we're going to return false. Because as we said before, if it's true, it keeps the values. If it's false, it doesn't. So if the UTXO, if the output that we are evaluating right now is not a script, we don't care about that. That's just a random output. So we're going to return false, and by returning false, we are removing it from the final list. And now we get only the ones that are actually scripts. So we could be creating a transaction that based on multiple different scripts, different stuff. So I could do in Cardano, it's highly parallelizable in the transaction. So you could be doing like, if the validators don't restrict you so heavily, like I'm doing right now, actually, you could like compose validators and use them like at the same time with the same transaction. So you could be, in theory, paying to other scripts. But we don't care about all the scripts. We're only about the one that has the correct hash. So we're going to, from the script credential, get the output hash, the output hash of this specific output that we're evaluating right now. And now we only need to check that the output hash is the same as the Oracle hash. If the output hash is the same as the Oracle hash, it means that this is an output that we are creating in the Oracle validator. So it returns true, and that output is kept in the final list. So if we save, this should, and here I have to add to do context transaction output. Let's see. I found this correct expression. Okay, so I'm evaluating this list, but I'm not giving a name. So let's say let's Oracle outputs equals. So now it has a name. And this is not needed. So we have a list of Oracle outputs. And we know that the Oracle needs to have the NFT. And anything created in the Oracle that doesn't have the NFT is something that we really don't care about. And because the NFT is just one, we cannot create two outputs containing the same NFT. So we know that this list, that this filter should return just one Oracle output, because the NFT couldn't be in two outputs at the same time. So this Oracle output, let's see if it says here. It doesn't, but this is a list. We just filtered a list of outputs. So this Oracle output is of type list of outputs. But we know that this should contain only one. So we can, again, partially pattern match. We can expect that the list of Oracle outputs contains
You close, yeah.
a single, and this, thank you, Karina, a single Oracle output. So now, if I'm filtering the list and I have more than one Oracle output, I just fail. I just fail because I know that it's something is wrong. This doesn't restrict you from creating outputs in other wallets or creating outputs in other scripts that are not the Oracle output. But it does restrict you to only create a single Oracle output. So now that we have the Oracle output, same as we did before, we have to check that with the quantity of the value the quantity of the NFT is 1. So we could copy and paste actually. Let's be lazy. Expect that Oracle output has exactly 1 NFT. So instead of Oracle input is Oracle output. And this is already on output. And I think this should be fine. Yep. Okay. So this is the same check as before. So I'm not going to go over it again. We just get the amount of tokens that are actually NFTs. And because we know that it's an NFT, there should be exactly 1. If it's missing, it's wrong, because then if we create the output without the NFT, no one is going to find it. And it's possible to have 2 because there's just 1. And if we have 1, that means that we took it from the previous Oracle as well. So we consume the 1 in the input to get it here in the output. So all good. We have 1 output, and that output contains 1 NFT. Seems like we are really in a good shape right now. So we checked that we are in the update case. The delete case, it just checks that the Oracle's owner's wallet, and that's it. But the update, it checks that the Oracle is here, that there's a single Oracle that it contains an NFT. We also check that there's a single output in the Oracle address and that it has an NFT. We didn't check that the Oracle's owner signed the transaction. So we have to check that as well. So we could rewrite the logic that we just right here in the delete, because when we delete, we also need it to be signed. But let's not repeat ourselves. So let's remove this from here and say, okay, if this is a spend transaction, let's create the check that is signed by operator. And here we can say, because we are going to share it between delete and update, we put it outside the pattern match. So it's signed by operator, and that's it. All good. I think this should be spend. Let's see, maybe we are missing something. I think I need 1 more. Yeah. So I needed 1 more bracket. So if we are spending, it doesn't matter if we're deleting or updating. In both cases, we need it to be signed by the operator. So we're just going to check that from the get-go. And here we could as well, this is a Boolean. So if we could, if we wanted, just to say, expect that the list was signed by the operator. And for delete, we can say fail. For example, so if we spend, we check that it was signed by the operator, and we expect that to be true. If it's not true, we just fail. Like we never check for the redeemer, if it's an update and delete, so we are actually like saving computation, although if it's going to fail, it's going to fail in the user's wallet, so it's the same. But we are like short-circuiting to early failure if the operator didn't sign. So we could do this. We could like do the same as I did before, name it and put it right here with the name. Both are fine. I think I personally like this one better. Only operator and delete or update. Yeah, so I think this will be fine. And actually, because delete is fail, we could do, yeah, this is fine. It's the same. So we could, yeah, it's the same. So we could expect, here we could change when redeemer is to expect update. But this is fine. Let's not over optimize things. So now in both cases, we are checking that the operator signed the transaction. So all good for now. The only thing that we still are not checking, and that is important, is that we create a valid datum, a valid for like a datum of the right shape to be able to be consumed, like to be able to be used as an integer. So we need to check that it's an integer, and this is a bit no, this is a bit involved, but nothing more complex than what we did so far. So we care about the datum. So let's say, let's check. We have the Oracle output because we already we already pattern match it for it right here. So we got the Oracle output that has the NFT because we checked that has the NFT. So now we need to check if that specific output that we already have has the correct datum. And we saw already, if we search for output, we saw already that we have the datum right here. So we can say is valid datum, for example. And so we check the datum. Let's see. Datum. Okay, so an output datum. So the datum could be either no datum. We could have the datum hash, and then we have to search for the actual datum in the body of the transaction. Or we could have the datum inline, and we could have like the actual data provided by this constructor. So we have to take into account all three cases. And because we can pattern match for all cases, we can say when Oracle output datum is, and in this case we can say no datum. It's no datum, datum hash, and inline datum. No datum to do, datum hash to do, inline datum to do. We have to import this. Datum.
Data parameter.
Sorry?
The datum hash need a param.
Oh, yes, you're right. And this inline datum as well. Thank you, Karina. Datum. Okay, I think we're good. So we have all three cases. Datum hash contains the datum hash. The inline datum contains the actual datum of this output. So if we have no datum, so if we create an Oracle output, it was signed by the Oracle owner with the NFT, all good, except that it has no datum. So no one is going to be able to read anything from the UTXO. So that's wrong. That it's likely a failure in the front end or the actual interface of the off-chain code. So we're going to fail in that case. So if there's no datum, like no information is going to be shared by the Oracle. So in this case, we're going to say false. We return false. That means that is validatum is false, so it's wrong. So here I just say is validatum question mark. Actually, because we return false here and false here, we can say expect Oracle output datum as correct shape, or more specifically, is a number. So here we can say expect like this. So expect that when the Oracle datum is no datum, it's false. When there's datum hash, we have to find the datum. There's a function for that, but let's first do the easiest one, which is that we already have the datum. Like we have the datum right here. We just need to check that has the correct shape. How do we do that? So there's actually a really simple way. All we need to do is to expect that the rate has of the shape rate, and the datum, this is the datum. So if we expect, we have to read, this doesn't end in, yeah, so we have to return some Boolean. So I'm going to return true. So what I'm doing right here, expect, as you can see, is a really useful keyword. So in this case, I'm doing something different. I'm asking Aiken to parse whatever this data type we said, I think in the first or in the second lesson, we said that data is anything that could be encoded into Bluetooth Core. So anything that could be represented in a validator could be represented as data. But we don't want anything. We want specifically the rate. So we're going to expect the rate, and we're going to indicate the type that we're expecting. We're expecting that the type is rate. If we don't do this, this doesn't make any sense because we are not telling what shape is the one that we want. So we are actually telling explicitly, I want this to have the shape of rate, which is just an integer. And it's going to try to parse datum to rate. And if it fails, it's going to fail. And if it succeeds, it keeps going. If it succeeds, it has the correct shape because it's an integer. It's the rate. So I'm good. So then I add this true at the end because this expects a Boolean because we are returning a Boolean here, and we will return a Boolean here. We have to return Boolean in all cases. So if we pass this parsing without failing, we return true because the datum has the correct shape. Does it make sense? So this is like a third use of expect. So now we have to do the same for the datum hash. The difference is that we have to actually obtain the datum first. So how we can obtain the datum? Well, it's really easy. We just use the find datum function. The find datum takes a list of outputs, takes a dictionary of datums and a datum hash, and returns an optional value. It tries to find the datum, and if it finds it, awesome, like, or good. If it not, the hash doesn't correspond, like the datum wasn't provided in the body of this function. So like we cannot be sure that this datum hash actually represents an integer. So we're going to fail. So we have to make sure that we can get the datum before making sure that it's an integer. So it takes find datum, it takes a list of outputs, a dictionary of datum that we're going to see how we can find that, and a datum hash. So we have 2 out of 3. So let's do that. Let's say, okay, I have the datum hash provided by this constructor. So now I'm going to find datum, and I'm going to provide the list of outputs. We already have the single output that is the only one that is allowed by this validator, is the Oracle only output, this one. So we know that that's the only one that's going to be allowed either way. So we're going to just wrap the Oracle output in a list. So we have a singleton list that contains only the output that we know that is going to be there. We need a dictionary of datums that we're going to see later how we get that, and datum hash. And we already have the datum hash, what just provided by this function. So by this constructor. So we find the datum. There you go. So now it's complaining because we are not returning a Boolean. So we're going to return true, dear love. So we can have so it works basically. And this is still wrong because we have to provide all the datums of the transaction as a dictionary. So where are these datums? Same place where everything else is. Transaction. Inside the transaction, we have the datums. Dictionary of hashes, of data. So this is exactly what we need, a dictionary of hashes of data. Of course, this is on purpose by the Akin developers. So we say context.transaction.datums, datum, and this should work. And now this find datum, what does it return? Should return a datum. Oh no, it returned a maybe datum. If this works, let's research. Find datum, optional data. So we can pattern match, same as always, or we can just expect that is some data, and this data is the same as we had here, but provided by the transaction, the body of the transaction. So we expect to find the datum. We don't expect that we could not. If we don't find the datum, we fail basically. So again, we partially pattern match and fail any other cases. If we don't find the datum, we won't be able to check that it has the correct shape because it's not there. So we're going to just fail. So this should be fine. But the thing is, now we are in the same boat as we were at the beginning of this match. We have the datum, but we're not sure if it has the correct shape. So we just copy, paste. And by expecting that this datum has the shape of rate of an integer, we make sure that it's a value that is actually useful. So we checked everything. Let's go to the top. We checked. To delete the oracle, we only check that the operator must sign the transaction. We just did that. We just did that right here. And then if we update, we consume exactly one input. The input must contain an NFT. We produce exactly one output. The output must contain the NFT. The output datum must be an integer, and the transaction must be signed by the operator. The transaction signed by the operator checks before entering which the redeemer we are checking, so that should be perfect as well. So we did all the checks, but there's an error. So let's see what's the error. Update fails. Why? Because there's something here. And maybe it's this, because it seems weird. Let's say this is a valid output datum. And no, this is not the issue. I found an unexpected token. So this is a bracket stick. I'm sure. But I'm not sure when did I misbracket something. If I comment this part, this expect. Okay. Expect. True. Let's see. Okay. So far, so good. So there's something wrong in this definition. No. expect this goes to update. Perfect. So it should be here. And now I'm going to delete this. Let's check it. So, oh, here. Okay. Cool. And so I was missing actually some squiggly brackets. Okay, so, and now if let me try to do what I did before, expect, and remove this. This doesn't exist anymore. Yeah. So this is the thing, because we are expecting a bunch, we are failing during the process of validation. We are failing each time we are validating. At the end, we have nothing to return as Boolean. And we need to return a Boolean because the function Oracle, as we see here, has to return a Boolean. So if we passed all these expects and we didn't fail during the whole validation process, it means that it's all good, so we can just return true. This might feel a bit counterintuitive, but the alternative is to just create a bunch of let bindings like we did in previous lessons and add here like a bunch of unified checks. So both are fine. This one is arguably better. But yeah, I mean, both are fine. Like you shouldn't worry about optimizing too much. And if we are really optimizing, we should pattern match for everything that we use in the transaction at the very beginning, because like accessing the transaction is expensive. So actually we should be like pattern matching for datums and for transaction outputs and for everything at the very beginning of the update. So yeah, I mean, don't worry about over optimizing. Like try to understand like the logic itself. And then you will, after you are sure that it works, you can like optimize to the death. Okay, so that's it. Any questions about the actual validator itself? Now I'm going to run the off-chain code to actually create the transactions and use this validator. And I'm going to build it. Let's open a new one and say Aiken. And here is Aiken build help. We see that we have this filter traces option. And this could be 3 different values. That's sorry, here, trace level. Trace level can be 3 different values. Silent, which is disable all traces together. Compact, only line numbers. Or verbose, which is like everything that we write in the all the messages that we wrote are shown if it fails. So we could say Aiken build -t -t verbose. And we have warnings, which is okay, but we have the warning, which is interesting. So we have the warning that we are not using the datum. And that's fine, because the datum is not part of the validation. We just want to make sure that the datum shape is the correct one. But we don't use the value of datum itself. We don't want, I mean, we could say, okay, the datum should be bigger than 0 or something like that. And so you don't have negative values. But in our case, we don't care. So we can actually safely ignore datum. Here, if we go to the top, we can safely ignore datum. And here. And we can ignore the value rate. There you go. And it will be fine because we're just checking the shape, but we're not using the rate, we're not using datum. So let's do this again. There you go. So we have 0 warnings, 0 errors, and it compiled. So we are ready to start using it. Should we start? We have half an hour left. If anyone wants to have like a 5-minute break, else I will just keep going.
Well, would you still make it in 25 minutes? Or is the time?
I think we have only half an hour, or I'm mistaken.
Yeah, but I mean, if you have 5 minutes break, you would have 25 minutes left. So the
Yes.
question is, do we need the extra 5 minutes?
I think we're going to be fine. Yeah.
Yeah, then let's have a break, 5 minutes,
Okay.
right?
Yes. Perfect. Okay.
Okay.
See you everyone in 5.
Yep.
Okay.
Okay, should we keep going?
Yes.
Awesome. So let's do the transactions now. If we go to the deploy Oracle script, we see that, as I said before, we need to first create the NFT. So in this case, Bob is going to deploy the NFT. Then it's the same that is going to actually operate the Oracle. So we get Bob's credentials, and then we query all the UTXOs that Bob has. If it has at least one, that means that it has money. So let's use that one. And then we provide the minting policy parameters, same as we did in the minting policy. We get the minting NFT policy from lesson 3. We apply the parameters with parameters, the output reference, the unique output reference that we're going to consume right now, and we're going to name it NFT. Then from this final script, this final policy, we're going to get the policy ID that we want to use for the parameters. We're going to get this could be defined previously and used twice, but it's okay. So we have the same name that we apply as parameters, the NFT name, and the token, as we saw before, is the NFT policy concatenated byte array concatenated with the NFT name. That's how we define a token, and that's what the two values that we represent in the asset class type. Then we're going to save the parameters to the Oracle parameters JSON file. We're going to save these ones because we're going to use these parameters in future in different scripts, and we don't have a global state here. So actually, I think already have it. I already have it, so I'm going to delete it. Oracle parameters, just in case. So we're going to generate it from scratch. Here we are writing the files, and we're going to print all three values. And then, I mean, we already finished with the NFT part, setting up the NFT part. Now we have to set up the Oracle part. So we're going to construct the NFT the same type that we define right here, the type asset class that takes the policy ID and the asset name. This is what we have right here. And then the parameters, as you can see in the Oracle, their parameters are the operator POKI hash and the asset class that we just defined. So that's the NFT asset class and the POKI hash. So it's a single constructor. So we have the parameters, the final parameters for the Oracle. We filter we get the script, the compiled code of the Oracle validator, and we apply the parameters to get the final Oracle validator that we're going to call validator. From this validator, we extract the address and we print the address, the Oracle address. Then we prepare two transactions. First, we're going to mint. In this transaction, we do everything in a single transaction. So we are going in the, I explained here, just so we are clear. When I explained, I said that the Oracles is going to mint the NFT to get the NFT, and then it's going to create the Oracle and send the value. But there's no reason that the Oracle owner can just mint the NFT at the same time that sending the NFT to the Oracle to create the Oracle. So these two transactions could be like bundled into one transaction. So that's what we do here. So we create a new transaction. This new transaction is going to mint one NFT. We provide nothing as redeemer. We're going to make sure that we're collecting the UTXO that the minting policy has to make sure that we are consuming for it to validate the transaction. We're going to attach the minting policy. And then we're going to pay to a contract. Instead of sending the NFT to ourselves, we're going to send it to the contract. Which contract? The Oracle address. And we're going to provide the datum. We're going to inline the datum. And we're going to provide the value 42 as our first initial value of the Oracle. So 42, the number 42 is going to be our first value. And as value, that this is the datum. As value, we're going to provide the NFT. The NFT that we just made. Instead of sending it to ourselves, we're going to straight up send it in the same transaction to the Oracle. So it's going to be there for the next transaction to check if it's there or not. So we're going to be able to use it. And that's it. We complete the transaction, sign, submit. And this is everything. So let's deploy the oracles. So here, run script, off-chain lesson 5. Deploy Oracle. And okay. There's an issue because I don't have the maestro key. I don't write. Yeah. But I do have Alice and Bob. Okay. So yeah. Let's see, how did we call this? Instance Lucid Maestro token. And now I have to fetch it. I forgot that I needed to create a new token. Copy. Oh, we are in preview.
Preview, yeah.
But well, okay, let's try. I may need to use preprod, but I don't remember, so. Wait, let's see now if it works. No.
I think, I'm not sure,
Yeah.
Rodino, if you have the correct order for the params. First you have, please.
The correct?
Yeah, first the NFT and then in the Oracle validator. Could you see the Oracle validator, please?
Deploy Oracle.
No, the validator in the file for the validator, the Oracle. Yeah. The params. You have first operator and then NFT.
Yes.
And in
the deploy, it's
deployed is
NFT and public hash. Do you mean this could be the wrong order? Let me think. Like this, do you mean? I do the operator NFT. I think it was. Let's try. No, but the issue is. Oh yes, I know what I have to do. Sorry, I have to rebuild the container because for it to pick up the environment variable.
Oh, yes.
Because the error I'm getting is way before this, is getting the minimum fee, which means that I'm not run script of chain. Yes, so it's 5. Okay. I don't remember minimum coefficient. Let's see. I know where it is. Here. Preview. Okay. Now I'm out of ideas, I think.
Sorry, what's the problem?
Run script. One second, off chain. Check wallets. Yes, I don't have Maestro token. Okay. Should I use quotes?
No, I don't think that's necessary.
And set
I see the problem. Okay.
and we are in preview, so we're good.
I mean, if it works, you must be able to know from the command line. You can just do echo
Yeah,
dollar
echo
master
the.
token. Dollar.
Oh yeah, I think I can do M.
That is.
Yes, there is. And let's try a run script off chain check wallet asset. Okay, good. It was without the double quotes. So now I can run script off chain lesson 5. But now the deploy Oracle. I'm not sure if this is right. Yes, but I think it's right. Deploy Oracle. Uncut cannot read properties of undefined compile code. Oracle. Lesson 6.
You are in the lesson 5?
Yes, it seems like I have to change this file. Okay, good. We deploy the Oracle. We have the policy. We have the name. We have the public key hash, the Oracle address. Copy the Oracle address and the transaction permission. So if we go to Cardano scan, here we have the address. It
You
has,
need to select preview.
yes. Thank you, Karina. I'm rushing and I do stuff wrongly when I rush. Okay, so we have the address, but there's nothing there because the transaction didn't land yet. But we can do is we have another script here that is called query oracle. And all we do is like we reconstruct the same, we reconstruct the oracle. And this is going to be wrong again because this is 5.
Yeah.
We reconstruct the oracle with the same values that we constructed the first time. So we take the values from this the oracle parameters JSON thingy, the file that we create. And then we try to find, create the oracle address. We try to find them, like again, all the UTXOs sitting at the oracle address. And from all the UTXO, find the one that contains the token, the NFT, the token, like the amounts of token of 1. This token is the actual asset. Go to the finisher. Is the actual asset of the NFT. So find the UTXO that contains the NFT. If it doesn't find it, this UTXO not found on the validator. Else, we're going to print the datum of this oracle. And this datum should contain, as of now, 42. So clear, and let's do run a script. Off-chain lesson 5. And we were querying the oracle. UTXO not found on the oracle. It's not yet there. There you go, it's there. So we have the NFT. We created the NFT. And if we go to the transaction details, UTXOs. I have a bunch of assets because I was playing around with other stuff. But the one that has the NFT that we care about has a datum attached. And if we click on the datum and we inspect the datum, we see that the datum contains 42, the value 42. So it's there. It's already, it's there. We just have to find it. And it doesn't find it for some reason. No, why it doesn't find it? Doesn't find it because we flipped the arguments. Pubkey hash. Oh, I'm scrolling. And now it finds it. So we have the data in Oracle is 42. So now other validators can on-chain take this information and validate their transaction based on that information by using a mechanic called reference input that we're going to see in the next lesson. Other validators can access this 42, can access this data without consuming the Oracle, because we know that if you are consuming the Oracle, that means that you are the owner and you are either deleting or updating, but not reading, because you don't need permission to read the datum of a UTXO. It's just there. You can just read it. So we're going to do that in the next lesson. We're going to see how we can read from this Oracle. But now it's the Oracle lesson. So let's update the Oracle. For the update script, we have the same logic as before, with the exception that we need to provide an argument, the new rate that we want to provide to the datum. So we do the whole thing. We have not much time, so we're going to keep going. We have to flip this because I wrote it differently the first time than the second time. And we get the UTXO, contains the oracle. We update the redeemer. And we create a new transaction. Before, when we queried, we didn't create a new transaction. We just got information from the chain, but we didn't modify the values on the chain. So we didn't consume or create UTXO, so we didn't need to create a new transaction. Now we do, because we want to change the value. We're going to collect the old, oracle, and we are going to provide the update redeemer, redeemer constructor. We're going to attach the oracle validator because the node needs to have the actual oracle to actually run the checks. We're going to pay the contract. Which contract? The same oracle. We're going to again pay to the oracle. We're going to pay the same NFT that we did before, but this time we're going to provide a new rate. And we have to add the owner of the oracle, Bob, the signature of Bob, to the transaction to make sure that the oracle validates the transaction. So we signed and complete. So
you need to, sorry, you need
Yeah.
to rename lesson 645.
Oh, thank you so much. 5, 6. There you go. Thank you, Karina. You're a lifesaver. So let's do this. So we want to run a script off-chain lesson 5. And as options, we have update oracle. And now I have to provide a number. Which number? Someone say, please, anyone can say a number. You have 1 minute. Okay. No one?
4.
Four.
No.
Awesome. 4. So we have a new value. So let's run this. Transaction was submitted. So we consume this UTXO. And actually, if we do quickly enough, we can run script, and we can lesson 5, and we can say query the oracle. Oh, already changed. So I wanted to show the 42 and then the 4, but it was fast enough. It was so fast that it's already updated. So the oracle now, instead of 42, has a 4. So we successfully updated and queried the new value of the oracle. And just as a proof that I'm not lying, before it was 42. And if we go to the transaction and we go to UTXOs, and we see that the output that we consume an output that had an NFT, and if we check the datum, we see that the datum was 42. And these are the outputs. Here are the inputs. Here are the outputs. So as outputs, now we have an output in the same address with the NFT, but now it has a different datum, 4. So we successfully updated the oracle. And that's it. Any questions? Comments?
Amazing. Very good.
Thank you. Thank you so much, Lars. Okay, so yes, Anderson?
It's great stuff. I think I'll actually revisit it again. It looks very amazing, the way you've approached it.
Awesome. Thank you so much, Anderson. I'm glad. Okay, so next lesson, Friday, is going to be the last lesson. We're going to do a full, I think it's going to be last lesson unless Lars wants to do something else after this. We're going to do a full example of a stable coin using an oracle, like same as this one. And with a nice front end and stuff. So make sure to understand how the oracle works, at least in theory, because we're going to use it now. We're going to consume from an oracle. And that's it. Okay, so see you everyone on Friday.
Thank you very much.
Okay, thank you.
See you on Friday. Bye.
Okay,
Bye.
bye-bye.
Thank you.